Let's have a class. We will finish the lecture this week. I will put on the eCampus the practice exam over the weekend, and then you can do it. Next week, Tuesday, we will do a review, and Thursday we'll have an exam 1. Okay, it's the same place. Let's start from here. We still do the review what we talked. We spent time talking about the internal structure of bacteria. Cell wall, or we say membrane system. And we talked about the cell wall structure. We mentioned about the major thing is peptidoglycan, which is composed by N-acetylglucosamine cross-link N-acetylmuramic acid and with all kinds of the amino acids. And of course, we know gram-positive is sick, gram-negative is thin. Then we talk about the ribosome. We have subunits, which is a large, sorry, it's on top. We have a large subunits and small subunits, so it's 50S, 30S, and we combine it as 70S. And we said the S means the Vandenberg units, which is a precipitation velocity. So it's not a simply you add up together. And this is the place for protein synthesis. Or we say it is DNA translation. Then we talk about the DNA, RNA briefly. We talk about the chromosome, and we also talk about the plasmids. And we said the plasmid is usually a small base pair sequence on the chromosome, and typically for all plasmid, which is responsible for the antibiotic resistant. And then we also mentioned about the flagella. And we mentioned about there is 4 different types of the flagella, which is amphitrichose, heterotrichose, lithotrichose, and peritrichose, heterotrichose. And this is for motility. And this motility is real motility. So we had a concept called chemotaxy, and this is always remember it is a round trip, which is bacteria attracted by the nutrients, but they also could be leaving away if you see in a stress environment or stress signal. Then we spending time talking about the endospore. For endospore, the key thing is right in the center. It is calcium dipropanic acids, and also very small soluble DNA protein because of the center, so they can resist and protected in the resistant and in the stress and also harsh environments. Okay, so this is the outline what we talked already. We're going to move on to today, which is bacterial growth, and we also mentioned briefly for the growth of bacterial cell. We talk about it's called binary fission. That means it is 1 becomes 2, 2 becomes 4, 4 becomes 8, so 2 times the power of n. And we also mentioned about the generation time. Generation time, which means doubling time. Doubling time indicate how long it's going to take one cell become two cells. Some of the bacteria are very short. Let's say E. coli, only 30 minutes. That's why we can grow in the lab. And some of the bacteria really take a long time. For example, Mycobacterial tuberculosis. It took 12, 24 hours to have one cell become two cells. That's why we need an acid-fast stain to do the presumptive determination in the clinical area. Okay, so we're going to move on today. This is a little bit of a mess, but we can explain to you because it is important, some of the concept. I want to explain also, we're going to use it in the lab too. So in the lab sections, when we do spread protein, pour protein for numeration bacteria. So this is what happened. The bacteria initial, let's say you have an N0. After certain time, which is T, it's going to become NT. Now how they do it, because we call it's a doubling time, or we say it's a binary fission. So that's multiplied by 2 times the power of n. So that's a basic formula. Now, in the microbiology numeration system, we transfer them to log. You know that in the mass, if you do log, they basically automatically become the same. Now, when we do log, here the log stands for log 10. So what is log 10? So for example, 10 to the power of 2, if we do this, log 10, that equals 2. Is that right? You should know about that. For example, log 10, 10 to the times power of 3, that equals 3. Now, why we have to use log? The reason is from the statistics reason. And it's because bacteria is huge. So, for example, I have 2 groups. Group A, group 1, group 2. Okay, I get doing some experiments. I come out with bacteria number. Okay, I have 10 to the power of 4, 10 to the power of 6, 4, 6. Let's still have this. Okay, I have another set of the bacteria. I have this. I have only 10. I have 10. I have 10 to the 7. These 2 groups, if you come out with this number, can we do a statistics analysis? The answer is no, because the error is too much. And you don't need to do statistics difference. It will no difference, because the error is too much. It's not follow normal distribution. Said very simple. So what we do, because it's huge, so we become log 10. Once we become log 10, this equals 5. This equals 4. This equals 6. This equals 3. And here the same thing. This equals 2. This equals 1. This also equals 1. And this equals 7. So instead of you compare these huge number, you compare these number. Now can we do statistics analysis with these 2 group of number? Yes, we can, because this is well controlled, the error. And they follow normal distribution. That's the reason. Because bacterial number is huge for most of the bacteria, except like Mycobacterial tuberculosis. That's why we change them to the log. Okay, once you change them to the log, how we do it? Log NT equals log N0 add log 2N. Now this is another mess. So for example, if you have, let's say, something like y equals x, z, then you do log y, that will be log x, z, This equals log x and log z. This is completely a mess, okay? Now we come here. This equals log n0, and you have n here, n becomes log 2. So then you can do some switch, which how you going to do switch, which means n equals log nt minus log n0, then divided by log 2. Now, what's the value of log 2? That means 10x equals 2. What is the x value? Around 0.301. And you know that if this, how many? Around 3.33-ish. Okay, so that's x. Now you do it. And at the same time, this n, which means how many generations it has. So we divide it by t. Once you divide it by t, comes out with an index is k. What this means? Which means it is a growth rate. Which means how fast it can grow after certain time. The certain time is t. Now we already know the log 2 equals 0.301. So this formula certainly could become k equals n divided by t equals log nt minus log n0 and divided by 0.301 and t. So that's its a general formula. Now, in some of the circumstances, we are talking about is generation time. And generation time also equals doubling time, which means how long it took one cell become two cells. So you can say it is like how long it takes one become two. Therefore, this t is become what? Is become g. That's a generation time. At the same time, this nt becomes what? 2 and 0. So this formula, if you change it, what it becomes? That k equals log 2 and 0 minus log n0 divided by 0.301 g. And you know this can comes out with log 2 and log n0 minus log n0, then becomes 0.g. And this is gone, and this is gone, so it becomes like that. That's a growth rate, is a reciprocal number of the doubling time. That's how we get it. And also we can do just a switch the doubling time, or we say generation time, is a reciprocal number of the growth curve, of the growth rate. The g equals 1 divided by k. I want to list it here because right now everybody talk about AI technology, talk about the machine learning technology. These are just a very basic model. If you are doing computer programming, these could be more developed. Because the bacterial growth curve is not really linear. I'll show you in a second. Then all kinds of the programming comes out. You have a different software. It is called predictive microbiology modeling, which is a very basic machine learning tool. We already have a lots of developed software. For example, like DM-FIT, like GENA-FIT, like USDA IPMP software. Those are all developed, could be analyzed, the bacterial growth situation. But they all comes out with the basic is on the slides. So how you calculate the growth rate and the generation time. So now it comes to our next question, how the bacteria grow. You should always remember the bacteria not grow like this. It's not always grow like it never ends, although it looks like it is huge. It is always a steps to grow, which means it's a phase-based growth curve. So what it looks like? We have x-axis and the y-axis. X-axis always is a time. That could be second, could be minute, or could be hour. And the y-axis is always the population. The population could be just a raw number, or it could be transferred to log 10 CFU. Could be per ml, per gram, all kinds of units. So what the curve looks like? The curve looks like this. It's 4-stage curve. First of all, at the very beginning, the bacteria does not grow. It is called lag phase. In the lag phase, usually bacteria go into a new environment. They need to accustom to all kinds of environment conditions, including we're going to mention about the temperature, pH, water activity, moisture, and also the other bacteria may be surrounded by. And their DNA and RNA has to be prepared. So they didn't grow at all. They only do the preparation. And that is called lag phase. Once they are accustomed to the situation or the environment surrounding that, they're going to grow dramatically. You see the curve in the second stage, it's very steep. This is called log phase. That's the reason we want to introduce this to you, we want to introduce here to you. Because they'll grow really dramatically. And you using raw number, it is too much or too many. So we use log, and even this phase we call it a log phase or explosionary phase. So that's grow dramatically. Okay, how they grow? Obviously, they're going to using nutrients. That's why we talk about the 3 and the 4 different methods for bacteria to get the nutrients. When they get the nutrients, they start to grow dramatically. But in a closed environment or in a limited environment, the nutrients going to be used up. And we also going to learn in the next time, in the future. The toxication material will come out. This isn't like you eat every day, but you go to restroom all the time. Same for the bacteria. They get nutrients, they also take out of the metabolic wastes. So, at some moment, the nutrients and the metabolic waste will reach equilibrium status. We can say it's a balanced status. So, they'll grow decreased or they become very flat. And this is called stationary phase. How many bacteria usually on the stationary phase? It's huge. Sometimes more than 10 to the power of 8 cells per ml, which means 8 log 10 CFU per ml. It is huge. Now, once the stationary phase has been reached, they started to survive there. But at that moment, all the nutrients have gone. Their environment building up or accumulated, the majority of those are waste. You can say bacteria poops. And it's a toxication for the bacteria to grow. So then the bacteria started to die. That's why the number going to decrease, and this is, we call it a death phase. So, bacterial growth have lag phase, log phase, stationary phase, and death phase. That is a balanced status between the nutrients and also the metabolic waste. Now, this is a very standard curve. and with these type of calculation. But in the real life, it could be complicated. So for example, I'm adding antimicrobials. Then the bacterial growth gonna slow or retard or like inhibit it. Then what happens? Then their lag phase maybe will be very long. Could be like that. And maybe because at the lag phase, lots of them are in the dormant status. They did not have to wake up. So maybe they grow short. The log phase time is very short. And maybe the stationary phase is short. And maybe they die more quickly. And these numbers, we all had modeling can do. All had a computerized modeling can do, and then we can transfer them into like a predictive models. Could predict in a certain environments how the bacteria grow. That is part of a very preliminary machine learning and AI technology. So that's why I want to introduce you here, especially in the food products, because food is a more dynamic matrix. The environment is changed all the time. Okay, so that's the basic for the bacterial growth, what the situation looks like. Here, which is come out with some of the concept we want to say. First thing first is called VBNC. That's viable but non-culturable. This is happening usually for the testing. So what happened is, what happened for the products? I'm using all kinds of methods, traditional methods, molecular methods to do the testing. But we didn't test it. Because our methods are limited, so we didn't test it. Or we cannot grow them in the bacterial medium. However, it existing as a toxication material on the food products. That is called a viable but non-culturable. Cell is alive but dormant. Second, bacterial death is not suddenly dead. It is also a programming procedure. Just want to let you know, that's why we call it a programmed cell death. That's another topic related to microbiology physiology, so we will just be briefly here. That could talk about the whole day. So keep in mind, some of the bacteria could be died. They cannot be cultivated, but the toxin is there, or they still existing, because every growing methods, they all have a limitation, and the bacterial death is a program. What we're going to spend today is we will be spending a huge time here talk about the factors going to affect microorganism growth. It sounds very routine and very easy. However, there is a story behind it. I want to explain the details. There are lots of the physics and the chemistry knowledge behind it. So you can imagine the factors to affect microorganism growth is pH, is temperature, water activity. That's a very tricky concept, and oxygen concentration. Seems like some bacteria need oxygen, some bacteria doesn't like oxygen, some bacteria need, but maybe doesn't like it, between the middle. So all these things we're going to talk about in very much in detail. First concept is relatively easy. It's called a pH. And we had a pH meter in the lab, and you did that in your lab too, in your chemistry lab. Let's say there is a juice products. You're going to measure the pH. There's a purified water or distilled water, you measure the pH. Certainly, bacterial growth in the environment, the pH is a major factor. So what is pH? It's minus log 10, the concentration of proton ions. That's called the pH. And the range is somehow between basically 0 to 14. Is that right? That not 0 to 10. It's 0 to 14. Right in the middle is 7. Here we say acid environment. This is we say neutral environments. And the last one we call it alkaline environments. Some of the bacteria like acid environments, some of the bacteria like alkaline environments, but most of the bacteria prefer neutral environments. So based on this category, we could categorize bacteria into acidophile. This is usually the bacteria survive 0 to 5.5 pH value. Most of the fungi can survive in these environments. Bacteria can survive, but their growth certainly is inhibited. Or some of them cannot, will be died. That's acidophile. Most of the bacteria we call it a neutrophile. They all survive the environments or grow environments is 5.5 to 8.0. Typically is good at approximately 7.0. That's why when we make a bacterial medium, we usually need to make sure add some buffer there, like let's say buffered peptone water or triphosphates, or we say PBS solution. We need to make sure the bacteria in their preferred environments, which is 7.0, because most of the bacteria are neutrophiles. Some of the bacteria can grow in the alkaline environments, which means hydroxy concentration going to be higher, OH concentration going to be high. This is, we call it alkaline file. Not many bacteria. Bacillus certainly loves it, and sometimes the fungi. But always remember, neutrophile for most of the bacteria. That is certainly understandable, and it's very nice. Because otherwise, in the lab, we have to adjust it to the pH below 7.0. That's always tough. So that's what the pH is. Now, what happened? In the real environment, we're not talking about the bacteria in the medium. In the real life, most of our pH, I would say, is around 5. It's slight acid. So for example, the distilled water, even the drinking water or pure water. And in the lab, you can test. You just take out of the water from the suppliers, or they say it's a distilled water. You measuring pH, it's not 7. It's about 5.5, sometimes 6.0, which means we call it a slightly acid. Now, is this the environment the bacteria can grow? Yes, of course they can grow. But here's another story. In the meat industry, when you buy a chicken, drumsticks or wings or a beef, they require you to do some of the intervention to killing or prevent foodborne pathogen. Lots of the time, they spray acid as an antimicrobials. Let's say lactic acid. Let's say citric acid. Now, why these things can kill bacteria? The reason is for bacteria of the cell, if you're coming with higher amounts of the protons, they will make bacteria highly energized. How they do? They need to repel these out. To repel these out, they require you ATP have to hydrolyze, become ADP, and phosphate rely on ATPase. If the bacteria keep doing this, like they are running 100 meters all the time, they will be exhausted. Sometimes they do not use this mechanism. They could switch with potassium to do the exchange of the protein to keep the balance. But what's the problem here is, whenever you use lactic acid or citric acids, basically the concentration is 2.5%. We will talk about this in the exam 2. This is we call sanitizing. It's not going to cure everything. So you maybe have 10 cells or 1 cell bacteria survive there. If they survive there, they certainly will resistant in this acid environment. Those we call acid-resistant cells. This will cause a huge problem. Because if the beef or the chicken products you further to do the cooking, they will resistant, generate cross-protection effects in the heated temperature. That gives you trouble, especially you're cooking a beef steaks. Let's say some more people are cooking 60 degrees Celsius. I want to make sure you have a juiciness. I want to make sure it's a tender. If normal bacteria, you can kill it. But for acid-resistant bacteria, no, it's not going to be. It's going to be survived there. I have done this research for many times. It will be survived there, so it gives you a challenge. So acid-resistant cells, that's a huge problem in the food industry and in the meat industry. So just want to let you know, pH is good. You controlling the pH in the environment is really helpful, but there is big disadvantage and the issue there for acid-resistant cells. Okay, so this is the first one. Second, the temperature. Regarding the temperature, I have some pre-knowledge I want to let you know. I originally coming from China, so I like to use degree Celsius. In here is degree Fahrenheit. Okay, how to calculate it? That is degree Celsius minus 32 multiplied by 5 and divided by 9. But both of these units is our regular or common recognized physics index. In the real physics area, what is the international standard for the temperature measurement? It's Kelvin. And Kelvin equals (273 at degrees Celsius). Okay, so just want to give you some of the basic knowledge behind it. Sometimes I use degree Celsius, most of the time. Sometimes I use degree Fahrenheit. But if we talk about in the exam 2, we will be introduced with the Kelvin. The Kelvin is different, a little bit different. It's a huge number a lot of the time. It's negative even. So bacteria rely on a certain temperature to grow. And because they wanted to make sure their enzyme is energized in a certain temperature, or we see the temperature range. So every bacteria, they have an optimal temperature to grow. They have some maximal allowed temperature to grow. If it's too hot, it will cause denaturing of their cell membrane system, which means they're going to die. If it's minimal, they're not going to activate their enzyme. So in a very low temperature, sometimes they don't grow. So every bacteria has minimal, maximal, and optimal temperature. So if we talk about temperature for bacteria, usually we mention about the range. What are the range? This is a good slide. There are 5 different categories. Psychrophiles, in the first one, the purple line here. This is usually very low temperature. It's in a deep ocean, in the Antarctic area. So those are usually we call environmental bacteria. You're not going to find it in the real life. Some bacteria can grow even minus 3 degrees, minus 5 degrees Celsius. It's almost like a chilling and ice temperature. Very few. The big issue happened in the food industry or in our real life is psychotrophs. This is called psychotroph. 0 to 30 degrees Celsius. Why? Cyclotroph, which means bacteria can grow at 5 degrees Celsius. What is that temperature? That temperature is a refrigerated temperature, if it's well controlled. If the bacteria can grow there, will give you trouble to storage food, which means using refrigerator will not inhibit the bacteria. They will start to grow. And there is a major risk for that is a pathogen, Listeria monocytogenes. This is a pathogen you heard about the news all the time. Why? Because it can grow at a refrigerated temperature. Let's say you have a ham, you have a hot dog. It's vacuum packaged. Even you see it's using antimicrobials. If it's contaminated with one cell of Listeria monocytogenes, it can grow in the refrigerator until usually 10 to the power of 5 or 6 cells, like a couple of days, even a week. Because they are cyclotrophs. Another one, it's a sporage bacteria, is Pseudomonas. It also can grow in the refrigerated temperature. If you buy a fish, let's say, a fish fillet, you put it in the refrigerator, even you use a film to pack it. 10 days later, you will see a lot of dots there. That's sporage bacteria, and it smells really bad because ammonia comes out. So just want to let you know, the bigger risk for our everyday life is cyclotrophs. Next one is mesophiles. Mesophile is relatively easy. This is the temperature range. Is most of us could be 15 to 45, I believe, 20 to 45. That is our majority of vegetative cell. And the foodborne pathogen is this range, like E. coli, salmonella. This gives us a risk too, because our skin temperature is about 35 degrees Celsius. Staphylococcus aureus, majority of foodborne pathogen or common bacteria is this range. Be careful about here. 45 degrees Celsius. That's warm water temperature. We will mention later on. In the food preparation, using warm water is a risk because that mild heat actually let the bacteria grow dramatically. If it's a pathogen. For example, you use 45 degrees Celsius to do the slaughtering of chicken. If the chicken contaminated with salmonella and you're processing 100 birds, not only you deactivate salmonella, you cultivation salmonella. And we say the whole process, it is an expensive incubator. So just want to let you know, most of the bacteria pathogen is mesophiles. Okay, next one, thermophile. Thermophile, they are actually heat resistant. So which bacteria? Bacillus is thermophile. They can survive in a relatively higher temperature. The last one, hyperthermophiles. They can up to 85, 113 degrees Celsius. One bacteria is hyperthermophile, Geobacillus. Why? Because there are certain genes which is resistant to the heat. That is the reason we can isolate its a special enzyme. The enzyme called TAC. Where is the TAC for? PCR reaction. You sometimes do PCR in the lab or even in the biotechnology classes. Where the TAC comes from? Comes from Geobacillus. Because Geobacillus is a hyperthermophiles. They can survive up to 113 degrees Celsius. What our PCR temperature? 94 degrees Celsius a lot of the time. The thermal cycle. So that's very useful for hyperthermophiles. The first person who isolated the tech from the hyperthermophiles is really smart because they get advantage of those special bacteria. Another place you can see hyperthermophiles is Yellowstone National Park in the hot springs. You see all those beautiful color. There are all kinds of bacteria is hot heat resistant. Which means if you get those bacteria, you isolate the enzymes. Obviously, those are hot resistant. So temperature range for bacterial growth, it's simple, but there is a lot to talk. Okay. We're going to spend a lot of time talking this guy. Water activity. This is a very tricky concept. And you heard about it in your chemistry class, biology class, lots of the time it talks very simple. And often the time it is mixed with another concept, means moisture content. So we want to talk about what is water activity. First question, what is moisture content? If we say moisture content of a food product, that means amount of the water. Now, of course, in your chemistry class, we'll talk about like dry base, wet base, all kinds of things. We skipped about that. Moisture content is amount of the water. Now, what is water activity? It's different. Water activity. We use acronym is AW. This equals, it is a ratio value. This called partial vapor pressure above a food product divided by partial vapor pressure of pure water. This sounds very tricky. What this means? So we have to explain to you. Okay? How we do this? Need some physics knowledge. In a closed vessel, let's say, a bucket. I put the water there. Okay, water molecule. What are they? Did you learn these? 109.4. This is called covalent bonds. And that's sigma next sigma plus. That's water molecular covalent bonds. And they connected with each other. Let's say another water molecule here, that's hydrogen bonds. Okay, that's water molecule looks like that. So, in a water environment, there are lots of these water molecules. They will evaporate or flee away from the surface. So they flee away. But at the same time, they also going to come back. So they go, they come back. After a certain time, they will reach equilibrium status. At this moment, there is a pressure up here. There is some of the pressure up here. This pressure called vapor pressure. Vapor pressure is affected by lots of the factors. Physics, we say PV, nRT, or we're going to skip talk about that. But obviously the temperature, is one of that. So if we heat it here, I add a Bunsen burner here, I heat it. What happened? The vapor pressure will be increased. And once the vapor pressure is equals atmosphere pressure, what will happen? The boiling will happen. Is that right? Water boiling will happen. That is called vapor pressure. So, by the way, the boiling temperature, the boiling point is related to elevation. So, usually the curve looks like this. This is the temperature. If you are, looks like that. Elevation, so it should be the other way. The y-axis is temperature. The x-axis is elevation, which means how high compared to the sea level. If it's 0, that is 100 degrees Celsius. And the curve looks like this. So, where are we? At Morgantown, we are at Appalachian Mountain. So our boiling temperature is about 94 degrees Celsius. It will start to bubbling and boiling. Let's say Rocky Mountain National Park at Colorado. It's about 90 degrees Celsius. How about the highest mountain in Nepal, the Everest, where it is? Right here, 70 degrees Celsius. Yeah, that's usually 70 degrees Celsius. So you put the eggs there. 70 degrees Celsius, not too boring. It's not gonna well cooked. That's called the vapor pressure to bring you concept of the boiling temperature. So that's what means vapor pressure right here. Now, in a food products, if we do the same thing, this is a pure water. So only water. Now, in a food products, what happens? You have a protein, you have salt, you have sugar, or you have other chemical ingredients. And there is a water molecule there. They're gonna go out, because in the food products you have protein, salt, sugar, they're gonna dragging them down more dramatically compared to the pure water system. Therefore, here you get less vapor pressure. So, this comes out with a water activity level. Water activity in a pure water, 1.00. Water activity in a hot dog, 0.995. That's why bacteria can survive, can grow, because lots of water activity. Water activity in a beef jerky, 0.900, because beef jerky or some sausage is dry. Water activity in, let's say, chips, or a bag of chips, that's only 0.250. So what is water activity? Available of water, bacteria can use. Said very simple. That is what activity. Now we back to the concept. We are talking about water activity. What's the relationship between moisture content and water activity? It's a very tricky question. I will do a little bit more explanation for you because it is an important concept. you should know, although it's a little bit extends the microbiology area. X-axis, water activity. Y-axis, moisture content. We also call it equilibrium moisture content. Let's say I have a food product, a starch. Okay, I'm putting a little bit of humidified environments. I will do a research how they absorb the water, how they dissolve the water. The curve looks like this. This is absorption, and this is desorption. And I can separate them into these. This is 0, 0.25, 0.75. Very simple to let you know. Our water products, when they absorb water and dissolve water, we say absorption, desorption is not reversible. We want it to be reversible. So think about, if I have a beef, I don't want a bacteria to grow. I take all the water out. If one day I want to cook it, I put all the water back. Is that a good idea? Yes, because we never will have an issue of acid resistance. Because bacteria will never have a amount of the water to grow. But is that possible? No, because it's not reversible. So I'm going to skip the principle behind it about that, okay? Just want to let you know, a water product's absorption, desorption is not the same. It looks like that. Sigmoid the figure we call it. So there are some of the food products, their water activity is really relatively low, like here. What are they? Chips. So did you ever heard about the chips contaminated with bacteria? Yes, very few. You never heard about there is a AEM breaking news said 100,000 pounds of chips contaminated with Listeria monocytogenes. You never heard about that. Because this temperature, this water activity, it's not favorable for bacteria to grow. But chips, what do we care about? It's lipids oxidation. Because if the chips, you open the bag, it will become like sweetie. That's called flavor reversion. So we don't care about microorganisms. Did you ever eat chewy chocolate bar? Yeah, sometimes you eat that as an energy, prepare for the final exam. Chewy chocolate bar. Did you ever care about the bacterial growth? You never heard about there is a salmonella growing in a chewy chocolate bar cause a national outbreak or recalls. No. The reason is this area is also not favorable pathogen to grow. What we care? Why the chocolate bar is brownish color? That's Maillard reaction. Is that right? That's chemistry. How about meat? How about vegetables? Yeah, you hear about those outbreaks every single day, almost. Because this is favorable for bacteria to grow. Looks like that. So this is a very typical curve in a food chemistry area, which is talk about the relationship between water activity and moisture content. And what this tells you, some food products, it's linear. Some are not. Some are really flat. But the way what we have is our everyday life we touched the meat and the vegetables. They are huge amounts of the water activity. And their relationship with moisture content is always linear. So giving you a very wrong impression, which makes you think water activity is similar to moisture content, but actually it is not. Okay. Other things we mentioned about here is relatively humidity, that is 100 multiplied by water activity. So this is sometimes is in the textbook, there is a little bit disadvantages. You take out all these items from a microQ, most standardized for the microbiology textbook. They will tell you what activity is listed on these. But I don't think you understand it. Because especially with vapor pressure, it's very hard. It's a physics knowledge behind it. And what's the correlation between what activity and the moisture content? It deserves a certain paragraph to explain it. Because this is the most tricky one. Even for our graduate students, because we had a water activity machine in the lab. It cost $4,000, sometimes $10,000. You just cut the meat, you put in. After 5 minutes, beeping, oh, the data comes out, then you record it. But the principle behind that is relatively complicated. Okay, here is a picture which just tells you if you have unbalanced the dissolved compounds in the bacterial environments, it's very similar to what you learned in the biochemistry or biology lab. It will shrink. That's called a plasmolysis. I call it a paralysis of a bacterial cell. This comes out with another thing. We most of the time using different salt concentration to make the standards of different water activity. And the bacteria sometimes like salt, sometimes doesn't like salt. If the bacteria can grow in a salt concentration more than 0.2 mole, what is mole? How to make 1 mole sodium chloride? Is that you measure that's molecular of salt, 35.4 is chloride, you add together, dissolved in 1 liter. That is called 1 mole. 1 mole equals, what is that called? Avogadro constant. So what means 1 mole? That is a standard. Is that right? That is a bridge index between molecular and our chemicals. So some bacteria can grow automatically at 0.2 mole. That's halophils. Which bacteria is halophile? Staphylococcus aureus. Why? They can grow very well on skin. Our skin has salt. That's why you do a half marathon. You're running half marathon. After a couple of hours after you're sweating, you see your t-shirt, there is a white line there. That is salt. And the skin has salt. Staphylococcus aureus will grow very well on the skin surface. That's why it is a halophils. Extreme halophils, if they can grow more than 2.0 mole, we barely don't see those in our everyday life. We only see that in a certain place, which is Salt Lake, Great Salt Lake City. In the Salt Lake, in Great Salt Lake City, I don't know whether you went there before. I went there a couple of times. It's lots of mosquitoes there. It's not very nice in the summertime. And the bacteria there pretty much are highly halophils. They're resistant to the salt. Okay, so the concept connected to what activity is the impacts of sodium chloride on the bacterial growth. Now, most of the time, we keep our salt in a neutral status. That's why we're using 0.9% sodium chloride. We call it a physiological saline, because we'll keep the osmotic balance of our cell membrane, also for the bacterial cell membrane cell wall system. Okay, next one. This is another tricky concept. The requirements of oxygen for bacteria to grow. We'll give you opening remarks, then the detail we'll talk on Thursday. oxygen. You look at the slides, it looks like complicated. The figure there's a letter there's a word there, there's a sentence there explain, blah blah blah. You know, seems like very will make you very nasty. I will say those slides. So we can separate them. These concepts to make sure it's easy. Bacteria requirements for oxygen, you can basically into 3 categories. The first one is aerobic bacteria, which means the bacteria must use oxygen to grow. Then, in opposite to that, you have anaerobic bacteria. That means bacteria have to grow in the environment absolutely no oxygen. Now, of course, there's something right in the middle, which means the bacteria can grow in the presence or absence of oxygen. That is called facultative. And most of our foodborne pathogens, Salmonella, Listeria, E. coli, it's facultative. That's why it is important. It is risk. Now, we go dig a little bit more. You grow in the presence of absence of oxygen, but does the oxygen help for? Yes. So, grow better with oxygen. Based on these 3 categories, we have some branch comes out. You have aerotolerant comes out. You have microaerophilic comes out. There are a big story up behind it because it's relied on superoxidized dismutase and catalase. There are lots of chemistry behind it. So we'll explain this to you on Thursday. Okay? Thank you.